Hello, first I would like to thank you for watching my presentation. I'm Sayanti Mukherjee, an assistant professor in the Industrial and Systems Engineering Department at the University at Buffalo, the State University of New York. The work that I will be presenting today is a collaborative project between the University at Buffalo and the Purdue University. This work has been recently published in the Applied Energy Journal, and the citation is provided here on this slide in case if you're more interested to learn more about the work. The title for today's presentation is Modeling Sectoral Electricity, Natural Gas Demand and Climate Nexus, a data-driven multivariate predictive framework. Now, as we all know, the different energy sources and the end-use energy sectors are highly interdependent. In this slide, this is a figure from the EIA website, which shows the different sources of energy like petroleum, natural gas, coal, renewable energy, nuclear, electric power, and how they are being consumed by the different end-use energy sectors. Now, if we focus on the natural gas, we see that most of the natural gas is being consumed by the electricity power plant and then the industrial, residential, and commercial sectors. To give more details about the distribution of natural gas supply, we see here, this is the data as of 2018. This is again from EIA, which is the US Energy Information and Administration's website. So as we can see here, the electric power plant consumes almost 35% of the natural gas, which is followed by the industrial sector and then followed by the residential and commercial sectors. Seeing the time trend from 1950 to 2018, we see that there's a clear increase in the natural gas consumption in the electric power sector. In fact, in the US, the natural gas consumption has increased by 3% in 2019, reaching a record of 85 billion cubic feet per day. However, in the other three sectors, especially the industrial, residential, and commercial sectors, the consumption has been pretty flat. That is, there is not much increase in the consumption. To take a further look into how these different energy sectors are interconnected, now natural gas is the primary source, as we already discussed. Natural gas supplies fuel to the electric power sector to generate electricity. For the residential sector, natural gas is mostly used for space and water heating and for use in some of the equipments. Similar for the commercial sector, it is mostly used for space and water heating and some equipments. In the industrial, it's mostly used for process heating, combined heat, and power system. On the other hand, now the electric power sector provides electricity to these three different end users: residential, commercial, and industrial. This electricity is mostly used for space cooling in the residential and commercial sectors, whereas a little portion of it is also used for space heating and water heating. In the industrial sector, on the other hand, electricity is mostly used for facility cooling, heating, and also ventilation. Thus, it is clearly evident that all these sectors and the different end users are extremely interdependent. The question becomes why it is important to consider this interdependency in the analysis of impacts of climate on the electricity or the natural gas sectors. It is already established fact that under climate change scenarios and deep uncertainties of the future, the entire energy sectors is going to see a shift in demand. In fact, the expenditure for different energy sectors is going to increase significantly. So in this picture, we can see the county level median projected increase in energy expenditure is projected to increase significantly up to a change of almost 20% under the extreme climate change scenario, which is RCP 8.5. And this large increase in demands, if it's not planned for, then it might lead to inadequate supply of energy, and that might lead to prolonged brownouts and blackouts. To summarize, our research motivation is grounded on 5 key facts. The electricity and natural gas, which are the two most important energy types used for space conditioning, they are highly interdependent and they co-evolve. They are affected differentially by climate and climatic change as well. Now, projecting long-term climate-induced demand trends in these energy sectors is highly complex and complicated. Significant climate-induced demand shifts can transform existing energy structure. And finally, not incorporating adequate climate information in the demand modeling might lead to suboptimal decision-making. There are significant research studies which has focused on establishing the relationship of climate on these energy demands, but there are several gaps. One, the conventionally used linear models are inadequate to capture the complex, potentially non-linear climate energy demand nexus. Also, none of the previous studies have considered the coupled nature of electricity and natural gas. Most of the studies, mostly on electricity demand and few on natural gas demand, they have developed separate demand models. Now, what are the limitations of using these separate demand models? These demand models cannot capture the complex interdependencies of the coupled electricity and natural gas demands. This can consequently underestimate the impact of certain common climate factors on the energy sector, which may lead to suboptimal decision making. Thus, our research objectives are to address gaps that we explained in our previous slide. So the first research objective is to develop generalized probabilistic models to characterize the stochastic and complex nexus of the nonlinear climate sensitivities in the sectoral electricity and natural gas demands. Second, we propose a non-parametric multivariate tree boosting method to overcome the issues of modeling climate sensitivities of coupled electricity and natural gas demands in an isolated way. Our objective was to identify the key climate and socioeconomic predictors that cause both the electricity and natural gas induced demands to co-vary. And finally, detecting the predictors with nonlinear effects and interactions without specification of such effects. To establish this framework, we selected the state of New York for our case study. The major reasons being the state of New York is the largest northeastern state, ranking 4th most populous state in the US and having the 3rd largest economy. Also, it is the 5th largest natural gas consumer in the US as of 2017. Majority of this natural gas consumption is attributed towards electric power generation and space heating during the colder months. However, 40% of the New York State's net electricity generation also comes from natural gas. In fact, more than 50% of the New York State's generating capacity is at the natural gas-fired power plants, while more than 33% of the capacity is at units with dual fuel capability that can use either natural gas or fuel oil. We collected data from multiple sources to achieve our objectives and develop our data-driven multivariate predictive model. Our response variable is obviously the natural gas and electricity consumption, and while we use different predictor variables such as the natural gas and electricity price, the precipitation, temperatures, wind speeds, socioeconomic features, and so on. This is some of the details about the trends in electricity demand across the various months in a year. It's not only electricity but also the natural gas demand, so we compare both in the same figure. So here the first one is from the residential demand and the second one is the commercial. In the first graph we see that the electricity demand peaks in the summer while natural gas demand is the lowest during the summer, and we see a similar trend in the commercial sector as well. Here we see the first figure is for the industrial sector. Here it's very interesting, as I already mentioned, that electricity and the natural gas, they are mostly used for industrial purposes and not for like process heating, cooling equipments and so on, and not for space cooling and heating. Thus we don't see much seasonal trend in the electricity demand. In fact, it has been well established in our previous research that industrial electricity demand is very insensitive to climate. On the other hand, in the electric power plant, the natural gas demand peaks during the summer. This is a mirror reflection of the electricity demand in the residential and commercial sectors. This indicates that the natural gas consumption in the electric power plant increases because of the higher demand of the electricity during the summer months. In this plot, we see how the different types of demands are distributed in the different end-use sectors. So to proceed with our modeling, we did a seasonality adjustment and detrended the response variable. The major objective was to isolate the climate-induced effect from this energy demand and be able to predict the long-term demands under the climate change. This is a correlation plot just to show you that the different energy demands that we were discussing are significantly correlated, and thus we propose to develop a multivariate model so that it can capture the correlation structure between these dependent variables. So to summarize, the different types of models we developed is residential sector, commercial sector, industrial and electric power plant sectors, and we did it for both the electricity demand and the natural gas demands. Thus, this electricity demand and natural gas demands from these four sectors constitutes our 7 response variables. We developed multivariate model as well as univariate model to compare the results. This is the overall research framework. Essentially, it shows that here in the model development framework, the first part is mostly based on the data collection from different sources, adjusting the seasonality trends in the response variable, doing spatiotemporal aggregation, then seasonal separation, and then leading to developing the final data set for our analysis. In dividing the data set into training and test set, and then did several simulations to train our model and test our model on a different data set to estimate the model performance, from which we selected the best model, and which finally led to our different statistical inferencing, like developing the variable importance plots, partial dependence plots, and then comparing the model with the multivariate model with the univariate models. So these are the results from our analysis. This shows that the model performances in the residential natural gas use in the intermediate months is slightly better than the multivariate model than in the univariate model. So essentially we developed models for 3 different seasons, like the intermediate season including the fall and spring, the summer and the winter, and we found that the model performance in general is best for the intermediate season, followed by the summer and then the winter. This indicates that how important it is to capture the energy demand shifts during this intermediate season. The root mean square, so in this case, as in the intermediate season, as we found that the slightly better than in the multivariate model than the univariate model, although the difference apparently seems not that much. It's a 15%, like the RMSEs are like in the multivariate model is like 0.053 compared to the univariate model, which is 0.062. This indicates a 15% difference in the predictive accuracy. This could mean an underestimation of more than 4,500 million cubic feet in natural gas demand in an average month, and almost 322 million cubic meter of deficiency of natural gas in a peak month, which is significantly high, and it should be, if it's not planned ahead in time, then there might be significant consequence in the natural gas supply. From the model, we also obtain the heat maps, which essentially shows the relative importance of the different variables in the various electricity sectors. So here, axis, we have the various responses, whereas on the y-axis, we have the different variables, the predictors, which are found to be important for all these sectors. Now, how to interpret this graph? As we see, these numbers shows the relative importance of these variables. When we sum these numbers across the columns, then we can see what variable is more important than the other, considering the entire energy sector. For example, for the dew point temperature, we have a sum of 248. Now, so this indicates that dew point temperature is the most important, and this is the highest sum. So I'm just showing it for an example. So dew point temperature is the most important climate predictor for these different energy sectors in the intermediate months. Now, among this, we see that 67 is the highest number, which means that dew point is most important for residential natural gas demand. That is, the influence of dew point temperature is significant on the residential natural gas demand. As a second example, we found that the season to date heating degree days with a sum of 193 is the second important variable. So we can see apparently, like, the darker shades means that they are more important, right? So clearly it shows that dew point temperature and season to date heating degree days are most important variables. Now, when we look at individual sectors, then we see that season to heating degree days is most important for the commercial electricity demand. The next question is how these variables vary. So we can also see the marginal effects of this climate predictors on the energy demand. So for example, here in this graph we see that the dew point temperature, as the dew point temperature increases, the residential natural gas demand decreases. So this means this is during the summer, which makes sense. For the season to date heating degree days, we see a similar trend for commercial electricity demand. What it means that with the increase in heating degree days, that is the winter, the commercial electricity demand decreases, which makes sense because as we discussed before, electricity is mostly used for space cooling, whereas natural gas is mostly used for space heating. Similarly, for the summer months, when we focused on the climate predictors, we season to date cooling degree days with the sum of 269 is the most important variable, and it is significantly influencing the residential electricity demand. The next important climate variable was the number of days above 90 degrees Fahrenheit, and it has a significant influence on the industrial natural gas. Essentially, with the increase in cooling degree days, that is, hotter days in the summer, the residential electricity demand increases, and also for the number of degree days above 90 Fahrenheit, which is essentially summer again, the industrial natural gas demand also increases. Finally, we come to the winter months, where we see that among the climate predictors, dew point temperature is the most important variable, with its highest influence on the commercial natural gas sector, whereas the season heating degree days is the second most important climate variable, with its significant influence on the residential electricity demand. Again, here are the partial dependence plots. In the commercial natural gas, with the increase in dew point temperature, the demand decreases, whereas with the season to date heating degree days in the residential sector, as the season to date heating degree days decreases, then the residential electricity demand increases. Thus, and these are just some of the examples, but we can test these relationships for all the variables that we are interested. Finally, these are our key findings from the study. We performed a multi-sector assessment of the climate-sensitive portion of the New York State energy demand using a wide range of climate variables, including degree days, mean max temperatures, relative humidity, wind speeds, precipitation, etc. We found that integrated multivariate framework more accurately predicts the energy demand than the univariate model. The residential and commercial sectors' electricity demand are found to be more sensitive to heating degree days in a season. Now, the season-to-date heating and cooling degree days was also found to be critical across various seasons and also multiple sectors. The dew point temperature is crucial for predicting demand in the intermediate and winter months compared to the summer months. Our proposed framework is essential for the utilities that need to predict electricity natural gas coupled demand. We would like to acknowledge the support from Purdue University Center for Environment as well as the NSF grant. I would like to conclude the presentation. Here is my contact information. So if you have any questions, please feel free to shoot me an email. Thank you.